Chapter 10, we begin to look at systems where we're rotating instead of translating. Before, we only allowed a degree of freedom associated with motion, treating the objects as one point and allowing them to move to another point. In this case, we are now going to give an extra degree of freedom and permit these objects. We're going to only allow them to be rigid, but we're going to allow them to rotate in different directions. So again, what have we done up to this point? Well, we've essentially said we have these different objects. We're going to, force them to obey our different conservation laws. We're going to force them to undergo projectile motion, but we're going to treat them as though they're just points in space. And essentially, their center of masses can move from one point to another point, but that's all we're going to allow for them. In this chapter, we extend the idea that these objects can actually rotate in addition to move from point to point. But we do put the restriction on them that they're completely rigid, that they can't change shape, or essentially all the points on this object can rotate about some axis, but their distances have to remain constant. Now, when we talked about our motion in terms of translation, we used the symbol v. We had our velocity for using Cartesian coordinates that could be broken into three different orthogonal components, vx, vy, vz, and we could describe its motion completely in terms of what these different components were at any time. Now we're going to say not only can we move, but we can rotate about different directions, and we can have an x-axis, a y-axis, a z-axis, and this omega, this lowercase omega, represents how rapidly we are rotating about that axis. This is known as angular velocity. It has both direction and some magnitude. So as we rotate, it will rotate in terms of so many degrees per second, so many rotations per second, rotations per minute, or if we want to use the SI units, because the SI unit for time is the second, we are going to say radians per second. So radians per second are our SI unit. In 3 dimensions, we can have a rotational axis that is some component of these 3 directions, orthogonal directions. But that makes it rather complicated. We want to simplify our system in many cases such that we are going to we're going to change our coordinate system such that the rotation is going to be in the XY plane, and our axis of rotation, which is the direction that our angular velocity is going to point in, is going to be perpendicular to that, and thus it's going to be in the z direction. So first of all, you should be familiar with the radian. The radian is an angular unit. It is actually dimensionless. If we think about this, it has no distance. There is no time to it. But the radian represents the amount of rotation we need to get such that on a circle, the arc length on the circle is going to be equal to 1 radius, thus the term radian, 1 radius, and that comes out to be about 57.2958 degrees, or 57.3 if we want to round up. 1 complete rotation represents 2 pi, and what we're really doing is we're normalizing this unit of rotation to the circumference of a circle. We know the circumference of the circle is 2 pi r. Thus, when we make 1 complete rotation, we have moved around the circumference of the circle 1 complete cycle, if you will. Okay, so 2 pi radians represents a full rotation. 1 radian represents a rotation such that we've moved, if we're on the outer edge of a circle, we've moved a distance, an arc length distance s, equal to the radius of the circle. Okay, You're probably more used to using degrees, where they're 360 degrees in a full rotation. So obviously, when we make the conversion from degrees to radians, we can multiply by the ratio between one full rotation in degrees and one full rotation in radians, and that's how we get 57.3 degrees being equal to 1 radian. Now, there are a number of different measurements for rotation. This shows radians versus angles. And again, you should be very familiar with this. We know that if we go 90 degrees, that is equal to pi over 2 radians. 180 degrees, pi radians. 3 pi over 2 represents 270 degrees, and back to 360, we are at 2 pi radians. You should also know the more common angles, like 30 degrees is pi over 6, 45 degrees is pi over 4, 60 degrees is pi over 3. But again, we've used these quite a bit when we did different problems. Degrees we used quite a bit, but in terms of the radians, that's a more comfortable unit to use in terms of rotation because it gives us a very, we're going to see in later sections, it gives us a very easy transformation as we go from angular motion to translational motion on the outside of the circular motion. Again, 1 radian is 57.3 degrees. The conversion between radians and degrees, if you have your degrees already, I just like to, instead of doing 2 pi over 360, just multiply pi, divide by 180 degrees, because again, there's pi radians in a half a circle. A half a circle represents 180 degrees, and that gives us our transformation here. Again, if you have degrees and you divide by degrees and then you multiply by radians, you get back to radians. Both degrees and radians are dimensionless, though. So here's our conversion from radians to degrees. If we have 2.5 radians, that's 143 degrees. If we have pi over 3 radians, again, here we can see that that's 60 degrees. Here, again, we're converting from our radians to degrees. Going the other way, of course, we can see that 1 degree would therefore be pi radians divided by 160. So that represents almost 2/100ths of a radian. 1 degree is almost 2/100ths of a radian. So for instance, if I wanted to turn 23 degrees into radians, I would get 0.4014 radians. There are other obvious units for rotation other than degrees and radians. Degrees we probably used the most in previous chapters. Radians we're going to use more and more. There's actually something called a GRAD. Now, in all these cases, one complete rotation has been divided into equal parts. Degrees will separate the circle into 360 equal parts. Radians will separate the circle into 2 pi, equal parts. GRADs actually, it's used in engineering sometimes, but not as commonly anymore. Separates a circle into 400 parts. The idea that each quadrant is broken into 100 individual parts. So again, for 1 full rotation, it's 360 degrees, 2 pi radians, 400 GRADs. A half a turn is 180 degrees, pi radians, 200 GRADs. You'll see on some calculators, they still have GRAD. Do not put your calculator on that for any of these calculations. Now, let's talk about rotational quantities, describing rotation. The first thing we're going to talk about is angular displacement, which is normally written as either delta, theta, or just theta. That is the final rotational position minus the initial rotational position. It's the same thing as translational displacement. Delta x equals x final minus x initial. Here we want to know how much we've rotated in degrees. We take some reference mark, and the angle at which this is rotated through represents our angular displacement. Now, again, this disk isn't going anywhere. It's not translating any place. The center of rotation, O, is still at the center. But all the parts of the disk have moved apart around this point as the disk has rotated. And of course, the disk is completely rigid. So again, every point on the object undergoes circular motion about point O. If you're closer to the center, this point will have moved a smaller amount. If you're further, you're all the way out a distance equal to the radius of the disk, you have now moved along this arc length right here, which, if this in fact is 1 radian, would be equal to a total translational distance. Again, the distance, not the displacement, but the distance is moved, would be equal to 1 radian there. Again, we can talk about more complex behavior if we allow the body to be deformable, but that's really beyond what we cover in most introductory physics classes. So again, angular displacement, delta theta is equal to theta final minus theta initial. Usually we just write this as theta and we ignore the delta, much like we did with displacement. Eventually we ditched the delta sign and just wrote it as x. Also be aware that the direction is very important. We say that angular displacement is a vector. It has both direction and magnitude. If we're rotating counterclockwise, that is considered to be a positive displacement. And that has to do with the way that we've treated the angles previously. We always said the positive angles represented a rotation in the counterclockwise direction. If we go in the clockwise direction, clocks get it backwards, that represents a negative angular displacement. So clocks are always going in the negative angular direction, if you will. Obviously, if we have displacement, we can also talk about speed. There's angular speed and angular velocity. Angular speed just worries about how quickly the rotation is taking place. Angular velocity is worried about the direction and the amount. Okay, so if we're talking about angular speed, we don't worry about counterclockwise or clockwise. Again, remember, we've simplified our world from a three-dimensional world to a two-dimensional world, and we're saying the rotation can only happen in the XY plane. In this case, that really makes the rotation one-dimensional. You can only go forward or backward in terms of the rotation, counterclockwise or clockwise. So again, for our angular speed, our average angular speed, it's how much we move in terms of the angle divided by the time. To accurately do this, we probably want to have absolute value signs there because forward and backward motion isn't distinguished for speed. Instantaneous angular speed, the same thing we did for translational speed. At any moment when we want to know how quickly it's rotating, we take the infinitesimal change in the angle divided by the infinitesimal change in time. Just to give you some examples, the ancient CD player, back in the day, this was new for me, but the CD player has been supplanted by higher capacity storage. Now we normally use DVD equivalent for this. But the CD player, the old CD player would make about 3 to 8 revolutions per second. Eventually, this was supplemented at higher speeds. They tell you that, this is a CD player that operates at 12 times. It'd just be 12 times the number of revolutions per second. But here we see if we make 3 revolutions, that represents 2 pi times 3, or 6 pi radians per second. That would be 19 radians per second. At its peak speed, when it was reading the inside of the disk, it had to move faster to cover the same number of bits per second. That would be 16 pi radians every second, or 50 radians per second. DVD players, of course, replaced the old CD because they were higher capacity. They also moved faster with smaller bits burned onto their surfaces, actually embossed on their surfaces. It would make 10.5 to 25.5 rotations per second. This would be about 66 radians to 160 radians per second. Car engines, internal combustion engines, typically operate between 1,000 and 6,000 RPMs. I know 6,000 is a little bit much for your vehicle. You're probably going into the red when you do this. This translates to, if we divide rotations per minute, we divide by minutes per second, we get 16.7 to 100 rotations per second. And that gives us 105 to about 628 radians per second. So, in fact, if we look at RPMs, radians per second are a unit that are roughly about, 10 times larger. So if something is rotating about 100 radians per second, that's about 1,000 RPMs. If something's rotating about 600 radians per second, approximately, that's about 6,000 RPMs. So RPMs actually, translate, pretty well to radians per second. Okay, the GE90 gas turbine engine, which we bring up in a lot of our examples, is the largest gas turbine engine for airplanes. This rotates about 2,500 RPMs at full power. Again, if we want to convert this to rotations per second, that's 42.5 rotations per second. And if we want to translate that to radians per second, again, the RPMs, we can just divide by 10 roughly to get an approximate rotational velocity. And here, just some, different rotational speeds. We go around the sun. If we picture the Milky Way galaxies rotating on an axis, we rotate. Our solar system goes around, if we treat the Milky Way like a rigid disk, at 10 to the minus 16 radians per second. The moon around the Earth, 10 to the negative 6 radians per second. The minute hand on an analog clock, a milliradian per second, and seconds on an analog clock, basically a 1/10 of a radian per second, because it makes 1 RPM. Faster things, rotor blades on a helicopter. Here we have about about 47 radians per second. And we'll be talking about pulsars, especially when we get to angular momentum. There we have about 1,000 radians per second. Faster and faster, a dental drill. I know we all love these things. They spin at a very high rate of speed to reduce the amount of pain. That is 80,000 radians per second. And fastest that we've been able to get anything to rotate in the lab is about 6.3 mega radians per second. We want to use that. So again, the rotor on a helicopter turns about 320 RPMs. If we want to express that in radians per second, we need to do a conversion. if the rotor has a radius of 2 meters, what is the arc length does the tip of the blade go? And remember, a radian is for angular displacement, or I should say arc length movement. We have moved, equivalent, if we move 1 radian, equivalent to the arc length movement of the radius of the rotating structure. In this case, it's going to be a blade. It's going to be 2 meters long. So, first of all, turning RPMs into radians per second. Again, you can roughly divide by 10 to get more accurate. It's 2 pi radians for every revolution. It's 1 minute for every 60 seconds. The reason why we got about a factor of 10 is because 2 pi is roughly about 6, and we've got 60 seconds per minute. So we get 33.5 radians per second. Now, again, we are going to, get into, constant angular acceleration later on. But for a angle of change, we can say that omega is equal to delta theta over t. Therefore, delta theta is going to be equal to omega times t. And here we have, again, the rotational speed times the time that goes by. We will rotate through a total angle of 10 to the 4 radians. So if we want our arc length distance, okay, our distance in radians, okay, we just multiply it by the radius, by the number of radians, and that gives us the total distance that the blades have gone around on their tips, and that is 20,000 meters, or 20 kilometers in 300 seconds, 300 seconds. Now, again, angular velocity takes into account direction. It's a little bit strange to think that our angular velocity is not pointing in the direction of movement. It's actually pointing in the direction where movement is not taking place, because when this disk is rotating, if it's rotating the X and Y direction, all points on the disk are moving in the X and Y except for the axis itself, the center itself. But again, if you think about the way that we define a plane, and we do this in Calculus 3, we talk about the plane. The plane itself, if we have a vector defining that plane, and that vector is within the plane, that can be pointing in any direction. Okay. In fact, the plane of rotation represents an infinite number of vectors in the X and the Y direction. Okay. What is unique about the plane is the normal to the plane, and the angular velocity vector is perpendicular to the plane, or normal to the plane, to use more precise language. So if we take the cross product of the radius vector, okay, the position vector, points to some point on the outside of the disk, and we do the cross product of that point's velocity, okay, we get a vector which is perpendicular. Now, if we divide this by the velocity squared here, that will give us basically dimensionless unit. Well, it won't be dimensionless. It will be units 1 over time. And that again gives us a vector perpendicular to the plane of rotation there. So again, it does seem strange that the actual vector for rotational motion, the angular velocity vector, points in a direction where the motion is not. The motion is in the XY plane. But again, if we think about how we define planes, the normal of a plane is usually defining the direction that the plane is. So for instance, the XY plane, the normal for that would be in the Z direction. So once again, for angular velocity, just like with theta, if we have a Counterclockwise rotation, we say that our angular velocity is positive. If we have a clockwise rotation, we say the angular velocity is negative. If we're using Cartesian coordinates in 3 dimensions, again, we're looking down on the sheet of paper in the XY plane, we would say that the angular velocity comes out of the sheet of paper for counterclockwise rotation. It goes into the paper for clockwise rotation. And again, you can use the right-hand rule to help you with this. The rotation using your right hand, if you curl your fingers in the direction of rotation, the thumb will indicate the direction of your angular velocity. Finally, angular acceleration. Just like acceleration was the translational displacement divided by time, your average angular acceleration is going to be your change in your angular velocity divided by time. And if we do instantaneous, it's pretty much the same thing. So in these 2 examples, we have a positive angular velocity, just to keep everything simple. It's rotating in the counterclockwise direction, okay? So our angular velocity is in the positive z direction in both cases. If we're speeding up, however, this vector is getting larger and larger, so that indicates that our angular acceleration is also pointing in the positive z direction. This represents the rate that this vector changes. If this is pointing up, this vector is just going to get larger and larger and larger, because this times your change in time represents how much that vector changes. However, if our angular acceleration is negative, it points in the opposite direction of the angular velocity. So this vector will get smaller and smaller and smaller as the disk slows down. And again, we can think of a bicycle wheel as being an example of having, positive and negative angular velocity as it's rotating. If it's rotating faster, both vectors will be in the same direction. In this case, for a positive angular acceleration and a positive angular velocity, we're going counterclockwise. So our vector for both are pointing toward us. If it's slowing down, however, where it's going slower at the end, then the angular velocity vector is pointing at us. The angular acceleration vector is pointing toward us. Most cases, we're not going to be so concerned about the actual orientation of these vectors, because again, we're really reducing our motion to rotate in and inside the plane of our computer screen or the plane of our paper if we're doing this problem with pen and paper. In those particular cases, we worry about counterclockwise and clockwise being positive or negative. And again, as we take the limit for our change in time going to 0, we would say that our angular acceleration alpha is just d omega dt. Okay? I always have a little bit of a problem with angular acceleration because alpha looks so much like a that I oftentimes confuse the two when I'm writing them. So that's sort of unfortunate that when we start mixing translational and rotational motion, be careful not to mix your A's and your alphas up.